Okay, let's dive in. We're looking today at artificial intelligence. It's moving so fast, isn't it?
It really is. Feels like science fiction one minute, and then you realize it's, well, running half your apps.
Exactly. And we're using some great material here from Dr. Anthony Onoja at the University of Surrey to guide us.
Right. The idea is to go a bit deeper than the usual headlines.
Yeah, for you listening, if you follow AI, you know the basics. You want to get into the core concepts, the history.
And maybe understand why certain things developed the way they did. What are the underlying questions?
Precisely. Think of it as getting a focused take on the foundations and the journey AI's been on.
So you get that deeper understanding.
Okay, let's kick things off. Beyond just smart computers, what's the real essence? Dr. Anuja's material starts right there.
Well, at its heart, AI is this ambition, this science and engineering effort.
To do what, exactly?
To build systems that can do things normally needing human intelligence. Thinking, learning, perceiving, deciding.
And John McCarthy, way back in '56, he actually called it the art of making intelligent machines.
Yeah, that Dartmouth conference definition, it captures that creative spark, not just pure logic. It's about mimicking cognition.
So what makes an AI system, well, AI? What are the key traits?
You're generally looking for autonomy, so it operates without constant hand-holding.
Okay.
Adaptability, it learns, it gets better with data.
Right. Learning is key.
And some kind of reasoning, it tries to, figure things out, solve problems like a person might.
And you listening, you bump into this stuff all the time.
Oh, constantly. Your phone's voice assistant understanding your maybe slightly mumbled question.
Yeah, that's AI. Or Netflix suggesting that perfect weird documentary.
That's AI too, analyzing your habits. Or think bigger, like Tesla's autopilot figuring out traffic.
Or even in medicine, right? AI spotting things in scans.
Exactly. Spotting potential issues, sometimes faster or more accurately than the human eye. It's transforming fields.
Healthcare, finance, transport, entertainment. It makes these faster, smarter.
More efficient, definitely. Opens up new possibilities.
Now, you mentioned it's not just one thing. AI is like a family.
That's a good way to put it. Dr. Onoja's source uses this analogy of a tree, which I think is quite helpful.
Okay, walk us through that.
So the trunk, the main body that's AI itself, the whole big field, the overall goal of intelligent systems.
Got it. The foundation.
Then you've got these major branches coming off. A really important one is machine learning, ML.
Right, ML. We hear that term a lot.
It's a subset of AI where the system learns patterns from data, instead of programmers writing rules for every situation.
You feed it examples.
Exactly.
Yeah.
You give it data, and the algorithms find the patterns to make predictions or decisions.
Like predicting house prices.
Perfect example. You don't code if 3 bedrooms, add X amount. You feed it tons of past sales, data size, location, price.
And it learns the connections.
Precisely. Algorithms like, say, decision trees or gradient boosting figure out those complex relationships to predict prices for new listings. Learning from data is the core idea there.
Okay, so AI is the trunk, ML is a big branch. What about the leaves?
The leaves. That's where deep learning, DL, comes in. It's a specialized part of machine learning.
Specialized how?
It uses these complex structures called neural networks, often with many, many layers. That's the deep part.
And these handle really complex stuff.
Yeah, especially with raw data like images, sound, or text. Think facial recognition on your phone.
Or real-time translation apps.
Exactly. Or the large language models like GPT that can understand and generate text so impressively. That's powered by deep learning.
So AI is the broad umbrella. It can include older rule-based things.
Right. But ML is specifically about learning from data.
And DL is a type of ML using these deep neural nets needing huge amounts of data and computing power.
You've got it. Understanding those distinctions helps make sense of the landscape.
Okay, let's shift gears a bit. History. Where did this all start? It feels new, but the roots go way back.
They really do. Back to the 1950s, fundamentally.
Alan Turing, right, with his famous test.
Exactly. Asking that philosophical question. Could a machine think, or at least seem to think, like a human?
And then the actual term artificial intelligence was coined.
At that 1956 Dartmouth conference by John McCarthy, the official kickoff.
And early efforts were focused on logic, symbols.
Very much so. Symbolic AI, trying to represent knowledge with rules and logic, step-by-step reasoning. Huge optimism initially.
Then we jump to the 80s, and you get these expert systems.
Right, like MYCIN, the medical diagnosis one. They encoded human expert knowledge for specific tasks.
And they worked,
Impressively well within their narrow domains. But that was the catch narrow.
which led to problems.
Yeah, the so-called AI winters hit maybe starting late 80s into the 90s.
Winters, like funding dried up.
Pretty much. Expectations had gotten way ahead of reality. The systems were brittle, couldn't handle uncertainty. Compute power was still a bottleneck.
So a period of doubt set in.
Definitely. But research didn't stop. There were still milestones.
Like Deep Blue beating Kasparov in chess. That was 97.
Exactly. Chess is complex, but it has defined rules. It showed the power of search algorithms, even if it wasn't general intelligence.
So what turned things around? What ended the winter?
Two massive things, really, starting in the 2000s. First, the internet exploding meant suddenly there was data. Huge amounts of it.
Right, data to train on.
And second, computing power just kept getting faster and cheaper. Moore's law in action.
So the conditions were finally right for machine learning to take off.
Absolutely. Algorithms that learn from data became practical, powerful tools. Standard practice, really.
And then the 2010s. That
Yeah.
feels like when things went into overdrive with deep learning.
Totally transformative. You had breakthroughs like AlexNet in 2012 smashing image recognition benchmarks.
Showing what deep neural networks could do with images.
Yes, and then DeepMind's AlphaGo beating the world Go champion in 2016.
Go is way more complex than chess, right? More possibilities.
Vastly more. It showed DL could learn incredibly complex strategies, things humans hadn't even thought of. A real watershed moment.
And that brings us pretty much to now. The 2020s. AI feels everywhere.
It is. Generative models creating text, images, code, large language models powering chatbots.
It's more accessible, you could say.
In some ways, yes. But that power, that pervasiveness, also forces us to confront some really important questions.
Before we get to those big questions, let's touch on some foundational techniques Dr. Onoja mentions. Search algorithms.
Ah, yes, absolutely fundamental. Think of them as the tools AI uses to explore possibilities and find solutions.
Like finding the shortest red on a map.
Exactly. Or the best move in a game. Any problem where you need to navigate through options.
And there are different kinds. Some are simpler.
Right. You have uninformed searches, like breadth-first search. It just checks everything systematically, level by level.
Thorough, but maybe slow.
Can be very slow if the search space is huge.
Right.
Then you have informed searches. These are smarter.
How so?
They use heuristics, basically, educated guesses or rules of thumb to guide the search towards promising areas.
Like the A algorithm.
A is a classic, powerful example. It's used all over the place.
GPS navigation you mentioned? Video games.
Definitely. Pathfinding for characters in games. Logistics, robotics, any kind of planning.
What makes A so good?
It cleverly balances the actual cost to get to a certain point with an estimated cost to reach the goal from there, using that heuristic.
So it tries to find the best path, but efficiently.
Exactly. Optimal and efficient. It's really the backbone for a lot of AI planning and decision-making.
Okay, and the other foundation mentioned was expert systems. We touched on them in the history bit.
Right. They were a major focus in that earlier phase of AI. The goal was to capture human expertise digitally.
Like MYCIN for medical diagnosis. How did they actually work?
Typically, they had two main parts. A knowledge base, which stored facts and rules about a specific domain, like if symptom X and test Y, then likely condition Z.
Okay, the extra knowledge.
And an inference engine, which was the reasoning part. It applied those rules to the specific case data you fed it.
Plus some way for a user to interact with it.
Yes, a user interface. MyCIN apparently had over 450 rules for antibiotics, and its performance was comparable to human specialists in some tests.
Wow. Any other big successes?
Dendral was another early one for analyzing chemical structures. And XCon at DEC, which configured computer systems, reportedly saved them millions.
So they had real impact. What were their strengths and weaknesses?
Strengths. They could be quite powerful in their niche, and importantly, they were often explainable. You could usually trace the logic.
See which rules fire to get the answer.
Exactly. But the weaknesses were significant. They were brittle, step outside their narrow domain, and they broke.
Couldn't handle unexpected stuff.
No. And building that knowledge base. Hugely time-consuming, needed experts, difficult to maintain.
So ML has mostly replaced them.
For many, many tasks, yes. ML's ability to learn from data and generalize is just much more flexible and powerful for complex real-world problems. Though expert systems still exist in some specialized areas.
Okay, this brings us back to the present. All this history, these techniques. Why does understanding it matter so much now for you, the listener?
Because AI isn't just tech anymore. It's actively reshaping industries, society, maybe even how we think about intelligence itself.
And understanding the how helps grasp what the impact.
Precisely. And the potential is undeniable. Automating drudgery, boosting efficiency.
Finding patterns in data that humans just can't see.
Right. Accelerating science, potentially helping tackle massive challenges like climate change or disease. The upside is huge.
There's always a but.
There is. Dr. Onoja's material emphasizes this too, as is most serious AI research today. The flip side is critical.
These systems aren't neutral. They can inherit our biases.
Absolutely. Train an AI on biased historical data, say, for hiring, and it will learn and likely amplify those biases.
That's a huge problem.
It is. And then there are privacy concerns. Think about AI analyzing sensitive health data. The potential benefits are there, but so are the risks.
So it's not just about making AI smarter, it's about making it responsible.
Exactly. That leads directly to the need for ethical AI. We need systems that are fair, transparent, and accountable.
Fairness, meaning they don't discriminate.
Right. Transparency, meaning we can understand at least somewhat why they make the decisions they do. It can't just be a black box, especially for high-stakes decisions.
And accountability, knowing who's responsible if something goes wrong.
Yes. These aren't easy questions, technically or societally.
And this matters to you listening because...
Because you're interacting with these systems daily. You might work in an industry being changed by AI. You might even build or manage these systems one day.
So understanding the potential pitfalls, the ethical debates, it's essential for everyone.
It really is. It's about shaping how this powerful technology gets used. Dr. Onoja's material points towards practical engagement too, debating ethics, trying coding, comparing systems. It's an active understanding we need.
Okay, let's try and pull this all together, the big picture.
At its core, AI is about reasoning, learning, solving problems. That fundamental drive hasn't changed.
But the methods have evolved dramatically. Machine learning, deep learning, they've become dominant forces.
Powered by data and massive computation.
And the history shows it's not been a smooth ride. Visions, setbacks, those AI winters, but then huge breakthroughs.
Yeah, a very dynamic field. Foundations like search algorithms and even the lessons from expert systems paved the way.
And now ethical considerations aren't just an afterthought, they're central.
They have to be. Fairness, transparency, accountability, they're the guideposts we need as AI gets more capable.
So studying AI today, it's more than just learning code or algorithms.
Much more. It's about understanding a technology that's profoundly shaping our future and participating in the conversation about how we want that future to look.
So here's something to think about, building on Dr. Onoja's insights in this whole journey. Given AI's history of leaps forward, often driven by unexpected shifts like deep learning, what's the next potential paradigm shift simmering away in research labs right now? What might be the next deep learning moment we aren't quite seeing yet?
That's a great question. And tied to that maybe, how do we make sure that as AI gets even more autonomous, more adaptable, we successfully embed those crucial values, fairness, transparency, right into its core design from the start, not just patch them on later?
Definitely something to keep watching and thinking about.